A while back, I decided I wanted to learn more about controls, so I was watching some YouTube videos. One was about a PID controller that balances a ping pong ball on a track, so I figured I'd give it a try. The challenge is to design a system that can automatically move the ball from any position to the center of the track and keep it there. For example, let's say the ball starts on the left side. I can raise the left so the ball rolls toward the middle, but if that's all I do, it will roll too far. Instead, I need to raise the left, but then as the ball approaches the middle, I need to chip the track the other way so the ball doesn't go too far. Since there's not much friction, I basically need to constantly adjust to keep the ball in the middle. I can do this with my hand, but I want to build a robot that can do it for me. When I do it, my brain decides how much to move the track, my hand moves the track, and my eyes tell me how the ball has moved so I can make adjustments accordingly. Instead, I'll use an Arduino Nano as the brains of my device. This will use PID control. More on that later. The Arduino needs power, so I'll connect it to a 5-volt power supply. Next, I need sensors to tell me where the ball is. I'm using infrared sensors, one on either end of the track. These are both connected to the Arduino and the power supply. I'd like to power this with a 9-volt battery, so I'll need a voltage regulator and some capacitors to provide the right voltage. Finally, I'll use a servo motor to control the position of the track. This is connected to the Arduino and its own power supply. I've modeled this in CAD. You can see the sensors on either end of the track, as well as the servo which will control the track position. The track is made from extruded aluminum, and I 3D printed many of the parts. 3D printing is great because you can print exactly what you made in CAD and have it ready in just a few hours. Okay, now I have all the parts. I'm assembling everything with standard nuts and bolts from the hardware store. Since so much of this is 3D printed, it goes together just as it looks in the CAD model. Next, I need to connect the electronics. I used this little board to connect everything to the Arduino. And I printed various mounting points so I can secure the wires out of the way. After lots of troubleshooting, it's put together and working. Let's see how it performs. PID stands for Proportional Integral Derivative. These three factors inform the Arduino's decision on how to react to the ball's position. Let's look at these one at a time. When it's in proportional mode, the track moves proportionally to the ball's position. When the ball is on the far left, the left side of the track will raise, and when the ball is on the far right, the right side of the track will raise. As I move the ball back and forth, you can see the track adjusts proportionally to the position of the ball. By adjusting the proportional gain, I can change how dramatically the track reacts to the position of the ball. With a large gain, the track makes large adjustments, and with a smaller gain, the track makes smaller adjustments. Either way, the ball oscillates back and forth without stopping in the middle. This is why we also need a derivative term. Since the derivative of position is velocity, the derivative term acts to stop the velocity of the ball. Here I have the controller set to only derivative mode. Right now the ball has no velocity, so the track is not moving. However, if I push the ball to the left, I give the ball velocity. The servo will raise the left side of the track to stop the motion, then level out again as the ball comes to a stop. The same happens if I push the ball to the right. However, the ball does not necessarily stop in the middle. If I combine both the proportional and derivative gains, I have a PID controller. The proportional term pushes the ball to the center, and the derivative term slows it down so it doesn't overshoot. This controller is okay, but the ball doesn't always end up stopped exactly in the center. That's because the ball stops close enough to the center that the proportional term is only slightly tipping the track. There might be a piece of dust or some other factor stopping the ball from rolling to the center. Also, since the ball is stopped, the derivative term doesn't do anything. This is why we also need an integral term. The integral term is like the proportional term, but it increases over time. Take this exaggerated example of integral mode. I'm holding the ball off-center and the track adjusts more and more over time, attempting to move the ball until it rolls to the middle. Finally, if I tune all three terms and add them together, I have a PID controller. No matter what I do to the ball, it always ends up back in the center. We can also see what happens if the controller is improperly tuned. If the derivative gain is too low, the system is underdamped and the ball overshoots the middle several times. If the derivative gain is too high, the system is overdamped and the ball is stopped too soon and has a hard time making it to its destination. I can even change the code so the destination is somewhere else. For example, here's the controller with it set to 8 centimeters to the right. PID has countless applications, from complex self-driving cars to simple thermostats. I think it's pretty cool to see this demonstration in action. This project had lots of challenges. By far, the hardest part was getting good sensor readings. The control is easy when sensor input is good, but much harder when input is noisy. This caused problems especially for the derivative control. When the sensor value jumps around, the derivative term tries to react to those changes because it thinks the ball is rapidly making small but sudden movements. To address this, I used averaging schemes as filters, tested different sensor mounts, and made sure the servo and sensor power were independent of each other so that changing voltage draw from the servo did not affect sensor measurements. I also learned a lot about 3D printing after many failed and redesigned parts. In earlier stages of this project, the control was so bad that the track vibrated violently and broke many of my 3D prints. Along the way, I learned all about controls, Arduinos, electronics, and coding. Definitely a super fun project. Anyway, I hope you enjoyed this video. Thanks for watching.